All right, good good afternoon, everyone. We'll continue with diode analysis. In the first technique we look at today is a graphical technique known as load line analysis. Right. Okay, load line analysis. There we go. So, what is a load line, first of all? Well, we spoke about diode characteristic curves, right? Voltage on the x-axis and current on the y-axis. Current as a function of voltage. So, that characteristic will be very similar for diodes. So diodes manufactured in the same process. Okay, there will be minor variations because the fabrication or the manufacturing process cannot be controlled down to the atomic level. Okay, so even though two semiconductor devices are created right at the same time, right next to each other on the same material, the properties would be different to a certain extent. For the most part, the variations are very small. Okay, so if you have, let's say, 4 diodes in your lab kits, the operation or the VI characteristic for all 4 diodes will be very similar. There'll be slight differences, but within a small range of values, they will be very, very similar, exactly the same. Okay. When you take one diode and plug it into a circuit, the operation of that diode is influenced and constrained by the circuit parameters, meaning the external circuit places constraints on the operation of that diode. Okay, so this is the diode characteristic right here. And that represents this diode, right? So again, we don't know what the diode is. We don't know it's germanium, gallium arsenide, gallium nitride, whether it's silicon. We have no idea. We don't really care because we are provided with the diode characteristic. Function of current, current as a function of voltage. So if that is already given to us, we can design circuits to use the diode, and that circuit will place a constraint on the operation of the diode. And that constraint is known as the load line. So load line is the constraint placed on a diode by the external circuit. Okay, external circuit. To typically solve circuits using the load line method, we would have an equation for the characteristic, the device characteristic. In this case, it would be the diode equation. So we have one equation, right? We have two values or two variables, diode voltage and diode current. If you want to find the diode voltage and the diode current, we would need two equations because we need to solve two variables. So one equation will be the diode characteristic. The second equation we would generate from circuit analysis of the external circuit. Okay. Just as a brief refresher, in the first class of E201, you might have learned about circuit analysis. What is circuit analysis? Circuit analysis is basically the process of determining the unknown voltages and unknown currents in a circuit. That's all it is. Okay, so in this case, the unknown voltage is the diode voltage, the unknown current is the diode current. So if you have two unknowns, you need at least two equations. One equation would be the device equation, the other equation comes from the external circuit. So in a graphical method, we already have the diode equation plotted for us. All we need to do is plot the graphical representation of the external circuit, which is the load line. We can obtain by applying circuit analysis techniques to that external circuit. In this case, if we apply KVL to the external circuit, we can write an expression for the voltages that are present in the circuit. And I can state, now if you have a preferred method of writing KVL, you can do so. I typically start at the bottom left corner and I go clockwise. So I get minus VSS plus voltage across the resistor plus the diode voltage VD summing up to 0. And that gives me VSS is ID times R plus VD. Of course, this is a simple circuit, so we already know, if you have a single voltage source, must be divided across the resistor and the diode. Right? VSS is equal to resistor voltage plus the diode voltage. So now we have introduced ID and VD in this equation. But how can we plot when both of them are unknown to us? Yes. That's it. Plug in 0. So we can find the value for ID when VD is equal to 0. And we can find VD when ID is equal to 0. And that's it. Okay. And so we'll do that in just the next slide. But when we have those 2 points, and you can see here, it's point A, that's point B. If you plug in ID is equal to 0, VD is equal to VSS, right? No current is flowing through. Diode is off. That means all of the voltage is being dropped across the resistor, right? So diode voltage, sorry, if ID is equal to 0, VD is equal to VSS. And if VD is equal to 0, meaning there's no voltage across the diode, then the current is simply VSS divided by the resistance, VSS over R. All of the voltage is dropping across the resistor. Okay. And so we have 2 points, and those 2 points joined together give us the load line. So now we have 2 equations plotted out, and the intersection point of those 2 characteristics gives us a point known as the operating point. That operating point, the values of that operating point is the value for the diode voltage and the diode current. So the intersection point, which is right here, gives us VD and ID values. Okay, so the intersection point of the 2 lines or the 2 curves gives us the voltage for the diode and the voltage for the current. The value for the diode voltage and value for the diode current that is due to the external supply voltage VSS. Yes.
When graphing the diode characteristic, will we always just plot it based off like points and do like linear estimations between the points like in homework?
So the question being asked is if there is a question about plotting the diode characteristic or any plot for that matter, the answer would be yes. You just plot the 2 points, however far apart they may be spaced, and you just draw a line through them. Does it make sense? Any questions? Let's take a pause. Think over that. Let me know if you have any questions. All right, so question being asked is what do the subscript SS mean? That's simply a convention that carried over from different circuit analysis techniques, but in this case, it doesn't mean anything. The SS simply means supply voltage. It may as well just be VS instead of VSS. Okay, so it's just VS, supply voltage. It could be V in, could be VG, generator voltage, or it could just be V. Okay, so you notice that the intersection point is dependent on the values of VSS and R. If VSS changes, operating point changes. If R changes, the operating point changes, and or in any other component that may be in the circuit. So again, goes back to the initial point I made. The operating point, the load line is the constraint placed on the diode by the external circuit. So the operating point could move up or down the load line, right? The load line could be here. The operating point would be different. Could move up, and the operating point is now again different. So sorry, the operating point can move up or down the characteristic. Okay, up and down the characteristic. All right, let's take a look at a few examples. Let's say we have the same circuit as the previous one, and then the value for VSS is given to us, the value for R is given to us. If we like to solve this, then we simply plug in the values into the equation. So we would write an equation, and we would find, for example 1, if ID is equal to 0, then VD is equal to 2 volts. And if VD is equal to 0, then ID is 2 divided by 1000, 0.002 amps or 2 milliamps. Those will be the 2 points on the load line. Okay. How about the second one? I'll let you all do the second one. When ID is 0, what is the value of VD? I heard 10 volts. And when VD is 0, what is the value for ID? One milliamp. or 0.001. So let's do a plot. Let's do voltage D, current ID, and let's say, where are we going to put 10 volts? So let's say 10, 5, ID is in milliamps, VD is in volts. If I was to plot the load lines for these two, I would get, all right, first one is 2 milliamps and goes all the way to 2 volts. So since this is not to scale, and then the other one goes from 1 milliamp to 10. Okay, almost close enough to 10. Okay, this example 1, example 2. Here, if we had the same diode characteristic, we could actually take the intersection point and determine the operating point. Yes. So we have the question being asked is, why do we set VD and ID as 0? Is because we want to determine the voltage and current for a diode in a circuit. So if there are two unknown variables, then we need at least two equations to solve them. We have one equation from the diode characteristic, which is the diode equation. ID is equal to IS times E raised to, we saw that equation previously. And then when you connect the diode in an external circuit, that external circuit places constraint on the diode. So we can write a KVL or KCL equation for that external circuit, and we can generate a second equation. That second equation for this circuit gives us this. And in that second equation also, we have two unknown variables, ID and VD. So if we were trying to solve this analytically, we would have to solve this equation in conjunction with the diode equation. Okay. Graphically, the diode equation is already given to us. Okay. That's the diode characteristic. So if we plot this equation right here, that equation would intersect the diode characteristic, and that intersection point would give us the answers for VD and ID. But we cannot plot it without knowing the values for VD and ID. But for certain, we know that at some point, it should intersect the X and Y axis where VD is equal to 0 and ID is equal to 0. So if you plug in VD is equal to 0 into this equation, we obtain a value for ID. And when we plug in ID is equal to 0, we can obtain a value for VD. Now, taking that point further, it's not necessary that the circuit would work or operate at those extremes, but we just want theoretical values, right? As evidence, like the diode is operating right here in the middle. It's not operating all the way up here. It's not operating all the way down there. It's just theoretical values to determine the other value that is part of that equation. Yes. So operating point tells us the value of the diode voltage and current based on the operation of the circuit. So in general, if it's silicon diode, we'd say, okay, let's say if the diode is on, it's like 0.7 volts. But you put it in a circuit, apply 10 volts to it with 1 kilo ohm resistor, that 0.7 could be 0.71, could be 0.69, could be 0.68, could be 0.72, right? So it's the constraint placed on the diode or the device by the external circuit. So the operating point could go anywhere along the diode characteristic. If the external supply is only, let's say, half a volt, 0.5 volts, then it will be somewhere here along this line. But it would be a point on that line, right? If the external circuit is 10 volts, then it could be somewhere up here. We don't know. Make sense? So again, this is a graphical solution to determining the diode voltage and diode current in a circuit. Remember, when we had resistors in 201, EE201, you would apply KVL, KCL, Ohm's law, or any other analysis techniques to determine the voltage across that voltage across the resistor or current through that resistor. Same thing with the capacitor, same thing with the inductor. Now, instead of those components, we have diodes, we have transistors, we have op amps, but the techniques still remain the same, or the goal remains the same. We want to find the voltage across that diode. We want to find the current flowing through that diode. And those are the unknown quantities. Okay. Any other questions? Okay. All right. Let's look at a diode model. This is the ideal diode model. And what we do in the ideal diode model is we simply replace the diode with an open circuit or a short circuit. So if the diode is on, meaning it's forward bias, then we replace it with a short circuit. The diode is off, we replace it with an open circuit. Okay, OC and SC. OC and SC. The characteristic for an ideal diode are shown here in blue. Okay, if the diode is on, it's a short circuit. And when you have a short circuit, meaning both ends of the diode are now connected to each other, meaning there are two separate nodes connected by a wire, meaning they're the exact same electrical node, meaning there is no difference in electric potential between those 2 points, meaning the voltage between those 2 points is equal to 0, which is shown right here. VD is equal to 0. And if the diode is reverse bias, it's open circuit, no current can flow through. If no current can flow through, then ID is equal to 0. So an ideal diode, which of course doesn't exist, the ideal diode model, we simply replace the diode with an open circuit for off and short circuit for on. No other analysis required. It's a very quick and easy method to analyze any circuit. So typically, if we have circuits, the first thing I like to use is use the ideal diode model, determine which diodes are on and determine which are off. Then you redo the circuit. So if you have, for instance, for example, let's say multiple resistors and multiple diodes in the circuit, you would simply assume a state for the diode, either on or off, replace it with a short circuit or an open circuit, and then all you have left in the circuit are a bunch of resistors. And all you have to do is do circuit analysis to determine what those values are. Okay. So in an ideal diode model, what you would do is you would first assume a diode state. At the beginning, when you make these assumptions, those assumptions should be based on logic. If you're applying 10 volts to the anode and 5 volts to the cathode, 10 volts to the anode and 5 volts to the cathode, is the diode on or off? Is it forward bias or reverse bias? So we have a diode. This is the anode. This is the cathode. So for a diode to be forward bias, what must happen? I couldn't hear. What did you say? Current flows that way, but what must happen for a diode to be forward bias? Voltage must be higher. Anode must be at a higher potential than the cathode. Then the diode is forward bias. If the anode is less than the cathode, diode is reverse bias. Actually, this should be the other way around. If the anode is higher than the cathode, it is forward bias. If the anode is less than the cathode, then it's reverse bias. It's on, you replace it with a short circuit, it's off. Excuse me, you replace it with an open circuit. Okay. So at the beginning, you assume a diode state. It doesn't matter what you assume. Your assumption could be correct or incorrect at the end of the problem. It doesn't really matter. Okay. But having said that, if your assumption is incorrect at the end, then you have to go back, change your assumption, and start all over again. So when you make those assumptions, you want to base it on logic. Logic dictates that if the anode is at a higher potential than the cathode, the diode most likely is going to be on. Sometimes it's not as easy to simply look at a circuit and assume whether it's going to be on or off, especially if you have multiple resistors, multiple supplies, and multiple diodes in a circuit. So for every diode in a circuit, you would assume an on or an off state. If it's on, you replace it with a short circuit. If it's off, you replace it with an open circuit. Then you analyze the diode you're using any circuit analysis technique that come to that you feel is appropriate. You solve for the diode voltage and current. Now, when you solve for the diode voltage and current, which is right here, you go back here to this graph and you verify your answer. If your assumption was that the diode is on at the beginning, then logically it follows that the diode voltage must be 0. So your answer for the diode voltage must match with your initial assumption. I'll repeat. If you assume that your diode is on at the beginning of your analysis, then the logical answer should be that the diode voltage is 0 volts. So at the end of your analysis, if your initial assumption, which is right here, does not match, that means your assumption is incorrect, and you have to switch that. And in case of a diode, it's simple because it only has two states, either on or off. So voltage should be equal to 0. And if it's open, current must be 0. And we'll solve a few examples so that you can understand exactly what this means. Okay. So if it doesn't work, then you solve for the other steps. You repeat until your answers match your assumption. All right, questions? Shall we go to the examples? Okay. So here is the example diagram we have. So I want to point out, if you're taking the class online, please do not type because I am unable to monitor the chat window at all times. So feel free to speak up. We have a speaker in the classroom here. All right, let's see. Where's I? Okay. So the question being asked here was, since I'm already looking at it, if we treat an ideal diode as a short circuit, how could the voltage be different at the anode versus the cathode? And that's exactly the point. If the diode is a short circuit, then the voltage at the anode and the cathode is exactly the same, right? So then the potential difference between the 2 points is 0, hence VD is equal to 0. And then how is a diode turned on or off? Is it just by flipping the direction? Well, it's turned on or off. It's not turned on or off. It's basically what is given to us in the problem. In a real life circuit, of course, if you wanted to turn a diode on or off, you would simply take a look at the voltages at the anodes and cathodes, increase the voltage of the anode with respect to the cathode. It's now on. If it's the opposite, then it's off. All right, so example. All right, we got two diodes, two power supplies, and two resistors. Okay, we have to make assumptions on which diodes are on and which are off. So now let's say, let's make a cross matrix. We have D1 and D2, two possible states for both diodes, right? And so if we do a 2x2 cross matrix, we can have four possible combinations. Both diodes on or both diodes off, or either one is on and either one is off. So four possible combinations. So you have four possible analyses that you need to perform in order to find the actual values. Now, as I said, there's four possible states. If you choose the incorrect ones, you might have to perform four different analyses. So again, when you make your assumption, you always want to follow the logical methods and look at the circuit, see, make your best guess as to which diodes are on and off. So if you look here, what do we see? Voltage on the left is 10 volts. Voltage on the right is 3 volts. Right at the top, we know that the voltage on the left is higher, right? That is connected to the anode. The 10-volt source is connected to the anode of D1. I mean, there's a resistor in there, but it's connected to the anode of D1. So logic dictates, or at least I would logically conclude that D1 is on because the anode is higher than the cathode, right? And then on the other side, we have 3 volts on D2 and 10 volts on the other side. Again, we don't know the voltage drops, so D2 could be on, could be off. But my intuition just tells me that since it's 3 volts, less than 10, I'm just going to run with it and say it's off. Right? That makes the most logical sense. But let's say we choose D1 off and D2 on. Okay, D1 off and D2 on. So let's choose one state and go against intuition and logic. Now, if D1 is off, then it's replaced with an open circuit. And D2 is replaced with a short circuit. So if you redraw the circuit, you end up with this. Okay. So I'm going to say figure B. Figure B. So I want to go a bit slow and explain how we are replacing and what the replacement means. Okay. We are assuming D1 to be off. If D1 is off, we replace it with an open circuit, meaning we take D1 out, replace it with an open circuit. Off means the cathode of the diode D1 must have a higher voltage than the anode. Okay. So that means the diode voltage VD, excuse me, diode voltage VD is always taken with a positive reference at anode and negative at cathode. That means VD must be negative. Right? Cathode is higher than the anode. So the resulting value of VD must be negative. If it is not negative, then my assumption is incorrect. Make sense? Yes. VD1. Thank you. But in general, if my assumption is that a diode is off, that means cathode must be higher than the anode. That means VD should be negative or must be negative. And then if the diode is on, that means it's a short circuit. That means current is flowing through the circuit, and current flows from anode to cathode. So for an on diode, ID must have a positive value. Okay. So for off diode voltage, and I'm going to take out the subscript of 1, I'll say VD must be negative. And if it's on, ID must be positive. Anyway, so we make the replacements and we redraw the circuit. Once we redraw the circuit, that is shown, the resulting circuit is shown in figure B, which is right here. D1 off, D2 on. We analyze the circuit. It's a simple circuit because this is open, so there's no current flowing in the left half of the circuit. In the right half, 3 volts is applied to 6 kilo ohms. Apply Ohm's law, and you find, so analysis for figure B, you find ID2 as 3 divided by 6,000. And so 0.5 milliamps. Positive value. So far, so good. So far, so good. But how much is VD1? VD1 should have a negative value. So let's calculate VD1, right? ID2 is straightforward, Ohm's law. We got half a milliamp. Yes. No, in general. So the question again being asked is diode voltage and diode current. Are those assumptions, I mean, the conclusions valid for all diodes? The answer is yes. They are valid for all diodes. If you choose a diode to be on, then the voltage is 0 and current must be a positive value. If a diode is off, then the current is 0 and the voltage must be a negative value. So we can also go in this figure. ID is positive. VD is negative. Right. Okay. All right, so it's 0.5 amps, 0.5 milliamps. What is the voltage across the 6 kilo ohm resistor? Circuit analysis 201. If two nodes in parallel, 3 volts. The same exact nodes, right? So VD1, I can describe as the difference in electric potential between the 2 points. Point on the right, point on the left. Point on the left is 3 volts with respect to my common terminal right here at the bottom. This is 3 volts. So this point at the top is 3 volts. So the cathode of diode 1, cathode of diode 1 is held at 3 volts when you reference it to the lower node as ground. And then the anode, what is the value of the anode? 10 volts. It's an open circuit, no current flows. So the voltage at the resistor, at both ends of the resistor, is exactly the same. So it's 10 volts. So VD1 is 10 minus 3, which is 7 volts. More importantly, it's a positive voltage. If it is a positive voltage, that means my initial assumption is incorrect. Okay, initial assumption is incorrect. Okay. And of course, we kind of already knew that because at the beginning we said, we have 10 volts on the left, 3 volts on the right. It makes sense that D1 would be on and D2 would be off. But this is just to show you simpler circuit. We make an assumption, turns out to be wrong. So we go back and change our assumptions. Now in our second assumption, let's choose D1 to be on, D2 to be off. And so if D1 is on, it's replaced with a short circuit. And replaced with an open circuit, which leads us to figure C. And figure C, again, the same thing is repeated on the other side. If it's a short circuit, then ID1 must be a positive number and VD should be equal to 0. So ID1 is equal to 10 divided by 10,000. 0.1 milliamp. No, let's see, 4, 10, 10, 10 volts, 1 milliamp, not 0.1, 0.001 amps. And then we need to find the voltage. We know the anode of VD2 is at 3 volts. We just need to find the value at the cathode. So what do you think? How can we find the value of VD2 at the cathode? Voltage at or across the 6 kilo ohm resistor. And we can do that by simple voltage division. These resistors are in series with the 10 volt source. We can apply voltage division and determine the voltage across the 6 kilo ohm resistor. So VR6K simply be a fraction of 10 volts. Fraction is given by 4 to REQ, which is 10,000, 6 volts. And so the cathode is at 6 volts, the anode is at 3 volts. Therefore, VD2 is 3 minus 6, minus 3 volts, negative number. And because the diode voltage is negative, that verifies my initial assumption that D2 is off. Let's take a longer pause this time. Think over all of that. Let me know if you have any questions. Okay. Yes. So if I understand you correctly, the question being asked is, we have two diodes, we made two assumptions, right? We made one assumption for D1, we made one assumption for D2. One was correct, the other one was incorrect. Can we keep the correct portion of it? The answer is no, right? Did I understand it correctly? Yeah. So we can't. So the assumption is basically for both D1 and D2. If you have 4 diodes in there, and D1, D2, D3, D4, and you make assumption about the state of each diode, let's say 3 of the diodes are correct, but 1 is incorrect, that means all of them are incorrect. Okay, so if it's 4 diodes, it's 2 raised to 4. 16 possible states. So 16 possible analyses. But then, that wouldn't be. Let's just stop there. Yes. It's 10 over, 10, yes. So this is, yeah, that is correct. Yeah. Thank you for pointing that out. It is the resistor, not the other resistor. That would be current division. 10 times 6 divided by 10. Because we want to find the voltage across the 6,000 ohm resistor, not the 4,000. All right, does it make sense? Questions? No questions? Okay. All right, we'll end class here today. I'll pick up here on Friday. A couple of announcements. Homework due dates have been updated. So homework 2, homework 3, homework 4. Please check your calendar. Please check Pearson calendar. You can access Pearson directly. And when they are synced, it also shows up in your Canvas calendar also. Scan homework. Sometimes I may be a bit late in moving those around, but right now they're updated. Okay. So the scan homework assignments, even if they are showing like due right now or due in the future, your Pearson dates take priority. So if it's a Pearson date is like in 5 days, your scan homework also just take it 5 days. Okay. And then Friday quiz. As always, Friday will assess material from the previous Wednesday, Monday, and Friday. And then the Monday quiz will assess from the previous Friday, Wednesday, Monday. Okay. So this Friday's quiz will incorporate material from today's class, the Monday class, and then last Friday's class. Okay. All right. Well, it'll be a good day, and I'll see you all on Friday. Yes. Yeah. Let me stop.